I'm here at the studio of LSDI about to talk about Pangolin's new safety scan lenses for audience scanning. Now, Greg and I have done audience scanning measurements over many years, and we have documented within articles that Greg has written, within I've written, within an article and safety thesis that John O'Hagan has written about audience scanning and how it can be dangerous if not done correctly. Basically, what it comes down to is that the measurements that we have done over the years that we've repeated again today prove that if you want to do audience scanning as the laser beam comes straight out of the laser, you're basically stuck with about 10 milliwatts of light. And obviously that's not very visually effective, but that's safe. So the question is how to get higher brightness, a more effective show, at the same time as safety. The conclusion that we come up with in an article that Greg Makoff wrote called Art versus Science, and in a separate article that I wrote years later that appeared in the Laserist about how to do audience scanning safely, and then in a complete safety thesis that John O'Hagan wrote, was that the only way to get audience scanning to be safe is to increase the divergence. The problem is that if you increase the divergence over the entire scan field, it makes the lasers appear like they're being projected in clouds, like maybe you're in an airplane looking down at clouds or something like that. It makes it look very cottony or cloudy, and that's really takes away from the main intention and the effect that we as lasers want to accomplish. So earlier this year we came out with what we call Safety Scan Lens. It comes in this nice little kit like this, and we have a complete set of lenses, 6 to be exact. And what this is it's a half moon shaped lens where the lasers, as they're being projected, will project above the lens and not have any effect at all, so they will be at zero divergence increase above the head. So it'll be the maximum effectiveness, the typical laser show that you would normally see. Whereas down below the lens, the divergence is increased to increase audience safety. Now, an interesting thing happens when you project the lasers through this lens. It increases the divergence, but only within the audience area. And so the safety is increased within the audience area. And although the beams are more cloudy or fuzzy or out of focus down within the audience, the fact that the beams are still have low divergence above your head as you're watching the laser show, you really don't even consciously realize this and recognize this. So what we're going to be talking about today is how to install this on a projector, what this does, the various aspects of how it will affect the projection, and how to adjust this for maximum effectiveness. And we'll also be showing you a laser show with these lenses and without, so that you'll be able to see the difference and see exactly what a safe show looks like, what an unsafe show looks like, and so forth. Basically what we'll do is we will project an audience scanning show at 10 milliwatts, which is the safe level without the lens, and then we will increase the divergence with the lens, and then you'll be able to see that you get a dramatically better effect with the lens. So what we have in this kit are 6 different lenses. Each lens increases the divergence a little bit more, and these are numbers 1 through 6. A number 1 lens is the thinnest, and it increases the divergence just a little bit. It's mostly used for big outdoor shows where you don't really need too much of a divergence increase, or where the laser is very far from the audience. And we have a number 6, which increases the divergence quite a bit. It's the maximum that we have in stock here at Pangolin. And so it's a thicker lens because it needs to have more material to increase the divergence more. So what we've done is we put them all in this nice carrying case, and this foam is specially formulated foam that does not harm the lens, it doesn't outgas, and it just provides a nice carrying case. And this is especially handy when you're doing touring and things like that, where each next venue that you go to may require a different level of divergence to attain safety. So it makes it a very handy package. One of the things that we've done today, we've used both a quant laser, 2 separate quant lasers in fact, and we've used an RGB laser projector. And one of the things that we found is that there are some variations from laser to laser in terms of the beam divergence that comes out of the laser, because what these lenses do is they increase the divergence that the laser already has. So if the laser has lower divergence, naturally you might need a greater increase in divergence, and therefore you might need an actually even stronger lens. But this table can serve as a starting point of, well, this will get you in the ballpark. We would always recommend that you do measurements to make sure that you have the right lens for the job, but at least this table will kind of get you in the ballpark so that you choose the right lens for the job. So let me give you an example of what we found here. As I say, earlier today we've done some measurements. We have a Thorlabs high power meter here. We also have a very special irradiance meter from International Light, and we've done these measurements today confirming what we already knew, which is that if you don't use a lens, if you do not increase the divergence of the laser projector, you can only get away with about 10 milliwatts coming out of the laser projector. But using this RGB laser projector as an example, if we use our number 1 lens, we can increase the laser power to a whopping 15 milliwatts. But going up the scale to our number 6 lens, we can use the same RGB projector at 5 meters from the audience at a power level of 210 milliwatts. So 20 times more power than we could completely without a lens. Now, if we move this projector 10 meters away from the audience, which is at least a more realistic scenario, bigger room, so forth, again, with no lens at all, it's 10 milliwatts. But using up to our number 6 lens, you can operate that RGB laser projector at 870 milliwatts. Now, it's important to notice that what we're talking about is this is the power level, the actual power that you would measure with a power meter, but actually when projected down into the audience. This is a 2-watt RGB laser projector, so what we could have is we could have the entire 2 watts at low divergence above the heads of the audience, lowering the power to 870 milliwatts with our number 6 lens down in the audience. And how we would do that is with Pengulin's beam attenuation map technology. So basically, in many cases, you would be using both the beam attenuation map to reduce the power within the audience, and also a lens to increase the divergence within the audience. And in most cases, this would not even be noticeable to the audience that there's lower power, because the lasers are projecting at a downward angle through the fog with a forward scattering action that makes the beams look actually even brighter. Now, as I place the lens into the beam, one of the things that you notice is that as I move it upward, of course, it increases the divergence. That's what it's supposed to do. As I was saying in an earlier slide, I like to choose a pattern that has a central spar in it, so that as we move the lens left to right, we can orient this to make the center exactly perfect. Now, one of the things that this lens does, in addition to increasing the divergence, is it also increases the scan angle of the image. Now, when we sold these lenses to our first few clients and they noticed this in the projected image, they said, hey, this thing is increasing the scan angle of the projected image too. That's not right, or that's not desirable, or that'll never work. The thing is that as you're projecting this onto a surface, most definitely you see this wider scan angle. But in the projected imagery, in the audience scanning, you really can't tell that. And we'll see a real audience scanning laser show here in a second, and you'll see that even though the divergence is increased, and the reality is that the scan angle is also increased, is just not noticeable in normal audience scanning imagery. So the width increase really is not noticeable in normal audience scanning. To talk about this a little bit more, I could say that at our trade show booth in ProLight and Sound, where we had 6 laser projectors with 6 of these lenses on it, numerous experienced professional lasers came by our booth. People that did Muse World Tour and some of the top names in the entire industry. We're talking about Alberto Kellner, Hugo Bunk, Maurice Wartel came by to see the show. And before they saw the show, we didn't prompt them in any way. We just said, let us know what you think of this laser show. We'd like to hear what you think afterwards to see if they would detect anything objectionable. And at the end of the show, we'd ask them, did you notice anything? Was there anything strange or unusual about the show? And in most cases, they said no, they didn't notice anything. When they did say that they noticed something, they only said that they noticed that the show was more pleasant. So they didn't really say, oh, there's some sort of objectionable thing going on here. This is not a laser show. It was all very positive. So there's 3 important adjustments with respect to this lens and how it works. One of the adjustments is obvious. It's upward and downward. As you move the lens upward into the projected image, it will increase the divergence in the low part of the scan field where the lens is in place. So this is a pretty obvious, what we're doing here is just up and down. What might not be so obvious is left to right. As you move the lens left to right, what happens is the entire image will shift somewhat left to right. So what I do is I use a test pattern that has a clear central line in it, so that as I'm moving the lens left to right, I just line up that central line, and that lets me know that I have the lens in place. What's not so obvious is swinging the lens this way, this tilt effect here. As you tilt the lens, if the lens isn't precisely in a correct orientation horizontally, it's like skipping stones off the water. If the lens is tipped up too much this way, we get an upward facing ghost image. If the lens is tipped too far downward like that, you get kind of a downward facing ghost image. So it's only when the lens is precisely in the central position here, oriented this way, angularly, that you get perfect images out of this. Now what we've done with these lenses is we've created a lens mount that works perfectly on quant projectors. If you don't have a quant projector, that's okay, because it just uses 2 little screws, and it's pretty easy to mount 2 flat screws to your projector, which you can then attach this bracket to. But what this is it allows the lens to slide upward and downward into the scan field. And as you see, we also have this degree here where we can control the angle of the lens. And so once we get this directly in place, we just tighten up the screws, and then that will hold the lens in the precise orientation that we want. Okay, you've seen what laser shows look like at higher power coming directly out of the laser projector with the safety scan lens. Now what we've done is completely removed the safety scan lens, and we've adjusted the laser projector power to roughly 10 milliwatts. We're doing a safety measurement here with the meter to get to 10 milliwatts per square centimeter. So now you'll get to see what the laser show looks like with no safety scan lens involved and just the direct beam from the laser projector.